Okay, shall we continue? So we want to finish the mathematical properties of the matrix A that we got from the discretization of the Poisson equation. So the final property that we can state is that A has bandwidth. Ni. What does that mean? Let us remember our matrix A would look something like that. That we had the diagonal where we had the AP, we had the minus AE with some zeros in between where we have boundary conditions, and the minus AW with some zeros where we have boundary conditions tied to the diagonal, and then we had Ni minus 2 zeros, and then we had the AN, and then again here we had the AS. And if we count the number of off diagonals in here, we will find that this corresponds to Ni. When we also look on the other side, the number of off diagonals is Ni. And down here and up here we have zeros. We have in fact also zeros in between, but that is not decisive for the bandwidth. For the bandwidth it's decisive that everything that is then outside is zero. And the definition for the bandwidth is the following. We say that a matrix, general definition, A with the entries A, I, J has bandwidth W if the following condition holds, that is when the A, I, J is 0, whenever the difference in the coefficients I minus J is larger than W. So then we can find out that that is true because this is the A11, the A21, and this is the ANI plus 1, 1. So if we would write that here, we have here an ANI plus 1, 1. You see, if we take the difference of that, the difference between these indices I and J is Ni. So that is not 0. But if we go to the next one, Ni plus 2, 1, it is 0. So then this condition is satisfied. And you can prove that for all here, you can also do it on that side. So that means then that this matrix has the bandwidth Ni. And you can see it just by looking at the off diagonals, number of off diagonals where you have something, and the rest must be 0. So that is a typical for a sparse matrix. It's and then we have a band matrices. We usually have a sparse matrix. So then we know a little bit about the mathematical properties that will be useful when we solve the equations. We shall discuss that. Well, probably next week, but maybe we'll already start today with a simple case. But before doing that, we want to look into the case when we have not directly boundary conditions, but Neumann boundary conditions. So that will be the treatment of the Neumann boundary conditions. So we are again discussing the same problem that we are looking at, where we have the x and y, we have our domain, and we have our grid points. Let's see, first let's get some grid here. Equidistant. then that we have the notation is that we have the XA here, the XB here, the YC here, and the YD here. So that is the notation here. And now we want to discuss another case. And the following idea, we want to have now that we have on the left boundary, we have Dirichlet condition. Sorry, a Neumann condition, which we say Ux is equal to Ga. So it means the first derivative of u with respect to x is given as a function of y in that case. On the right-hand side, we want to keep the Dirichlet condition, that is u is equal to some function dB. And at the bottom boundary, we also want to keep the Neumann, the Dirichlet boundary condition, but we want to have a Neumann boundary condition at the upper boundary. Then the du dy is equal to some gd. So that means we decide on Neumann boundary conditions at the upper and left boundaries. By the way, could we have Neumann boundary conditions everywhere? Think of that for a moment. Could we have Neumann boundary conditions at all boundaries? We could, yes. But what's the problem with that? Remember, we are discussing uxx plus uyy is equal to f of xy, the Poisson equation. Imagine we had a solution to that. We had Neumann boundary conditions everywhere. So imagine that u is solution. Then I claim that u plus any constant is also a solution, if we had Neumann boundary conditions everywhere. Why? Because then the constant with second derivative will also be 0. And if this is entering in boundary conditions, it will be also fulfilled. So this cannot be okay, because then we would not get a unique solution. So then we cannot have this. So that means we cannot have Neumann boundary conditions at all boundaries. Because then the uniqueness would not be satisfied. By this argument, we could have done infinitely many solutions. So therefore, we want to have at least one Dirichlet boundary condition. So here we have two actually, at the lower and the right boundaries. So that is our assumption that we have here, that we have now Neumann boundary conditions. That is here the example that we consider. We have Neumann boundary conditions at left and upper boundaries. And we have Dirichlet boundary conditions at the right and the lower boundaries. So, and we can express that then also in the following form, that we say we have the du of xay dx is equal to a given function ga of y. That is at the left boundary. Neumann boundary condition. Dirichlet at the right, xb y is equal to gb of y. And that is true for y in the interval yc, yd. Now let's look at the others at the lower and upper boundaries. At the lower boundary, Dirichlet boundary conditions, that is u of x, y, c. So it's a given function gc of x. At the upper boundary we have a Neumann boundary condition du of x, y, d with respect to y is equal to a given function gd of x. And that is true for x in xa, xb. So then we have these boundary conditions, and then we want to decide, so we are then focusing here on these ones here, the Neumann boundary conditions, but we take the others with to have a complete picture. Now we want to decide on the grid points. The idea is to choose grid points where we really need to compute the Poisson equation. Where we have Dirichlet boundary conditions, we don't need it, because we have the solution. So let's see, the Dirichlet boundary conditions are here. And so there we don't need to do anything. Here. And we have Dirichlet boundary conditions down here. So there we don't need to do anything. But for the Neumann boundary conditions, we actually don't know the values. So that means here and here, we have to compute the solution. So also the Poisson equation is valid there. So we are going now to discretize the Poisson equation at the boundaries where we have Neumann boundary conditions. So that is the first decision. So it means this boundary and this boundary will be included. So and then we make them to grid points. And that we do by defining then the grid points in such a way that, say when we have here the I direction, that this will be I1, this will be INI. We take the J direction, we will start from here, from 1, and go to NJ here. So we will include now the boundaries as also with our grid points. So that then gives a little different definition of the grid points than we had for the pure Dirichlet boundary conditions that we discussed yesterday. So the grid points then can be defined in the following way, that we say the xi, grid point in the x direction, in our case we start from xa, plus, now we take it in this form, I minus 1 times delta x, and we let the I go from 1 to ni plus 1. And we choose as the delta x the grid spacing, in that case the difference, the length of the interval, which is xb minus xa, divided, now we have ni intervals. So that is different from what we had yesterday. You can check it when we have I equal to 1, we have here 0, we are at xa, so we have the left boundary included. When we take here the ni plus 1, we insert that, we get here ni here, times the divide times this gives then xp minus xa, we get xp. So that means the indices will then be the following. So this will be the index 1, 2, and so on. So we'll have some index I, and that will be the index ni, where we compute, and the index ni plus 1 will be at the boundary where we have the Dirichlet data. Okay, so then we do it in a similar way for the y direction. Yj is equal to, there we start by yc, and here we take now the j times delta y, and here the j is going from 0 up to nj. And the delta y in that case is the length of the interval in the y direction, that is yd minus yc. Now again we have here, now we have nj intervals there. And we check the the bounds j equal to 0 gives yc. So that is then, that will be the boundary where we have the Dirichlet here. Nj, we have Nj times delta y, then we get yd. So then we are up here where we have the Neumann boundary condition. So that means when we look at the indices in the j direction, we will have here index 0, 1, and so on. And the last one will be, so somewhere in between we have the j, and this will be the nj. So that means then for j equal nj, we are at the upper boundary where we use then the Neumann boundary conditions. So that is a particular way to focus on the unknowns. And the unknowns include now also the boundaries with the Neumann boundary conditions. That is the catch here. Now we look at these boundaries in one after the other. We start with this boundary here on the left. So, the Neumann boundary condition, left boundary. So let's see what is the situation. We have here our left boundary, this x equal xa, and we have some grid point, say 1j, and we have the neighbor, which is 2j. We have the northern neighbor, which is 1j plus 1, and the southern neighbor, which is 1j minus 1. So that are the, say, imagine that we are at some point here, and that we look what is around this. So we are focusing on this situation here. And now we want to discretize the Neumann boundary condition here at this point. So then the Neumann boundary condition at this point is du of xi, and that is then yj, if we are here, with respect to y. That is then given as a function, and this is the value. That is then approximated, that is one way we can do it, by second order central FEM. So we can try that at least. So we have then, we want to do a central discretization here. We need a point here. And then we simply, we have no point, but we imagine we have one. We had one. Then we start, we just shape, we imagine that we have a point there, which we call the ghost point. So we get here a ghost point. And that should have then the index 0j. We don't know it, but the condition will give us, Neumann boundary condition will give us a condition how to get it. So let's just try that. Doing the first central derivative involving these points, that would be then the u2j minus the u0j, so the boundary, the ghost point, divided by 2 delta x. That is then equal to ga of yj. That we can do. And from that, we can get then a condition what this ghost point value u0j should be. So let's see, that would be nice to have. So from that we get, from this approximation, we get the ghost point value. And that is then the U0J. If we just write out what it is the U2J minus 2 delta x times GA of YJ. So then we have that. And then we use it. And we use it in the formula for the discretization of the Poisson equation that we used in the interior. So this value for the ghost point can be used and is used in the equation 15, and there we use it for I equal to 1. So we have then, I write this equation 15 again for this case. 15 for I equal to 1 will give us minus AS U1J minus 1 minus the AW. Here is the guy that makes the difficulties, U0J. You see we will use that in here. Let's first write the whole equation, discrete equation. And we have the minus AB U2J minus the A north times the A2, let's see, I think this is U. U1J plus 1. And then on the right hand side we have the minus F of X1YJ. So that is the equation that we get if we take equation 15, the discrete form of the Poisson equation, and look for I equal to 1. And what we do now is we replace this here by what we have here on the right hand side. So inserting, that is 23, for U0J yields following. Let us first look at it. So if we can get this in here, we get here a U0J, a U20J. And that is the same as we have here, as we have here. So that means we can then combine the minus AW UT20J with the minus AE U2J. So we get another contribution for this value here. So then we will just change the matrix. The matrix will then be minus AE minus AW, because we then, that has entered here, and it has the same form as this. So we just merge that. And the right-hand side, this will go on the right-hand side, because we will then have the minus AW times this. That is something that we know. We just bring it on the other side, on the right-hand side. So that will be the change. And the rest is as it is, unchanged. So that means what we get from that is the following. We get 24. Most thing is unchanged. The AS, the U1J minus 1. And this is then used in here. So the next is already the AP. U1J minus AE times the U2J. And now comes the difference. We have already the AN is already here. No, let's see. Yeah, I think, yeah, I did an error. I went too fast because it is the AE. So this one here and this one here multiplied by the minus AW, that will also give a contribution. So that means we will have here, then the change will be that we add here the AW, U2J. So then we have that taken into account when we insert the U0J, the right-hand side, in here. So that is then taken into account, and the AN, we just take it unchanged, U1J plus 1, and the right-hand side we have the contribution that we had from the beginning, but now we have also this contribution here, because this contribution will also come in here, so we have a minus AW times minus this here, which gives a plus on the right hand side with a minus. So we get then, in addition to that, we get the minus. We have originally an AW here, and then this guy here, 2 delta x GA of yj. So that is also part of the right hand side. If we have the situation that the GA is 0, that is, we have, say, the homogeneous Neumann boundary condition, Ux equal to 0, then this term will simply vanish. But we have here the general case. So the change to what we had before is that now we have this is entering. Of course, we had replaced this here, so that is giving another contribution to the U2. And we have the right-hand side entering, because this, when inserted here, gives a contribution of the source term to the right-hand side. So, that is all. That means we have now a similar structure as we had before for the Dirichlet boundary conditions in the interior, but when we are close then to the left boundary, we have to take the boundary conditions into account in this way, that we modify the matrix. So the matrix then does not have minus AE in the diagonal, but minus AE plus AW, or say minus AE minus AW. So we have then to change the matrix. And we have to change the right-hand side. But only at the grid points that are then corresponding to the first, well, to the line x I equal to 1. Only there we have to do the changes. Otherwise, no changes are necessary. So then we have to discuss how to do these changes in the matrix. So then we can argue the following. The discrete form that we have here in the case that I is equal to 1, that can be implemented and that is in the form that we discussed yesterday, this block tridiagonal form, by using instead of the form 17a that was defining the diagonal entries, we use the following. It's 25a. We use what we call the dj, it was the diagonal entries, so that we zoom in then to the upper left corner of the matrix in the diagonal regarding the block. And then we had originally, we had the AP, and the left neighbor, or the right neighbor, was minus AE. And here we do the changes. So we have here then the minus AE minus, sorry, plus AW if you write in brackets here. So that is the change. So this guy enters at that point. So that is the change. And it will also enter later on, we shall see that on the right hand side. But first, this is the only change. The other parts of the matrix are completely unchanged. Minus AE, so that continues all the way down in the usual form, minus AE, AP minus AW. So that is the only change. So that is the only change that's happening. Otherwise, nothing. And that is then, but we have to do that for all the diagonal matrices, because they will all at this point make contact to the left boundary. And there we have to do that. So it will be from J from 1 to Nj. Then this matrix has to be modified. And the other thing is that we have then also to use change the right hand side. Let's see. That's what we need. The other changes is, so we continue the sentence for I equal 1, 24 for y equal 1 can be implemented into 16 by using so 17a this for the D matrices in the diagonal and using instead of plus, this is a little technical but you will see it. And we actually discussed it today for the block pentadiagonal form. So when this is appearing on the right hand side, that is in the Cj. And we had also discussed the C1 and the Cnj. We always have there this term appearing. So instead of that term, we use then the following one. That is, we use the term that is coming up here, that is the minus AW 2 delta x GA of YJ. And we do that for J from 1 to Nj. Everywhere where we make contact with the left boundary, or we are at the left boundary here, there we have to do this change. So that is all. So some change in the matrix and some change in the right hand side. So then we have discussed how to implement the Neumann boundary condition for the left boundary. Now we want to do the same thing for the upper boundary. Neumann boundary condition at the upper boundary. So there we have the following situation. We look at here we have the y equal to the yd, so we are at some point here, say y here, 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 and here. So we zoom in there. And then we have here the I and j. We have the I plus 1 nj. Here we have the I minus 1 nj. Then we have here a point involved. That will be the I nj minus 1. And you can already imagine what we do. We try to get a ghost point here. So that we get here 0. Sorry, that we get here I nj plus 1. Then we can do a central difference in the y direction for that around this point, I nj. So then we proceed in a similar way as before. The Neumann boundary condition at the upper boundary, which is then at xi yd, derivative is with respect to y, and the functional value is gd of xi. So that is approximated by central difference, and that will be then the ui nj plus 1. This minus this. Minus ui nj minus 1 divided by 2 delta y is equal to the given function value gd of xi. And from that we get the ghost point value. That we say the ui nj plus 1, which is outside of the points that we consider, is then equal to the ui nj minus 1. That is one of the points that we do consider. And now we get here a plus 2 delta y gd of xi. So then we'll use this again now in equation 15, as we did before. So let's do that. 26 is used in 15. And now we do it for j equal to nj. J equal to nj. Then we have the following. So maybe we can just do it as we come along this, where it pops up. So we have the 15 for this situation. Then we have here the minus as, the ui, and that will be then the nj minus 1. Will be our southern point value, minus the aw, the ai minus 1 nj, that is no problem, the ap, ai nj, no problem, minus the ae, ui plus 1 nj, no problem. But here we get to the problem, the an, and here we will have the ui nj plus 1. And that is the one that is outside. And for that, we shall use then the expression on the right hand side. Just let us continue, let us finish this. On the right hand side we will have the minus f of xi y and j. So now we will do the same thing. We will insert equation 26 for this here. And then we will see that we get here a contribution minus an ui nj minus 1. And that we have here. So then we can merge the minus in times this with this one here. So then we change the minus is in the minus is brackets plus an. So that will be what we do. So inserting 26 for the ui nj plus 1 yields then the following. And if you're in the matrix, it will be minus AS minus AN. And that will be then the U, I, N, J minus 1. And the rest is essentially unchanged. And let's see, then we have taken that replaced here. So then we will get also this contribution here. So we get minus IN times this contribution, and that will get then on the right hand side with a plus. So we'll have first the F, the minus F of xi, y, and j, but then we will also have on the right hand side the plus an 2 delta y and the gd of xi. We discussed. So that is what we have to do. That means for j equal to nj, we have then to use this equation for all the I. So that this can be implemented again into the form 16 by using, instead of instead of 17c for j equal to nj, the following. So the B matrix will be different. So that will be then the 28A, the B and J will then be, before we had there just the minus AS, now we have minus AS in this form minus plus AN. And then we have that in the diagonal all the way through to minus AS plus AN. The rest is 0, so that was just the diagonal matrix. And in the right hand side, that is in the C and J, we have to use, instead of the contribution AN GD of XI, we have to use the contribution that we have here on our right hand side. We have then to use AN 2 delta Y, the GD of XI. So that we have to do from 1 I equal 1 to NI. So that's all. And you shall look at that for the situation where you don't have directly the Neumann boundary condition at the upper boundary, but at the lower boundary. We shall not consider more than that. In the exercise 10, only the Neumann boundary conditions at the lower boundary. But you have seen now to do it at the upper boundary, and you have in addition, saw it in the beginning, have it at the left boundary. You can then also think yourself how to do it at the right boundary. So that means what it comes down to is implementing Neumann boundary conditions is to modifying the matrix a little bit near the boundary where it is relevant, and the right hand side if necessary. In our case, for the exercise, we will have an example where this is 0, so then a modification of the right hand side is even not necessary. Okay, so then we can stop here and continue next week by looking into the solution of the linear systems. Just one remark in the end, by doing this Neumann boundary condition implementation, we have destroyed the symmetry. If you think of it, if we have now in the matrix here it is not a problem, but for the other one it is a problem, because we have then the AS plus AN at the lower diagonal, and the upper diagonal we have just the minus AN. So we have no longer symmetric matrix. So that is the price we pay. But otherwise it's just changing the matrices and possibly the right hand side a little bit.